Madam, good morning.
Sir, video కూడా ఆన్ చేయరా? సార్ వినిపిస్తుందా? అది మ్యూట్ చేయండి.
మేడం నాయిస్ వస్తుంది మేడం. ఓకే, వినిపిస్తుంది. ఇప్పుడు ఓకే మేడం, ఇప్పుడు ఓకే. ఇంకో ఎక్కడ ఏమన్నా ఇవి ఆన్ చేశారా మేడం? బ్యాక్గ్రౌండ్ నాయిస్ వస్తుంది.
ఆఫ్ చేశాను సార్. ఇప్పుడు వస్తుందా?
ఓకే, ఇప్పుడు ఓకే మేడం, ఫైన్. ఎస్ సార్, ఎస్ సార్. గుడ్ మార్నింగ్ సార్.
ఇప్పుడు ఈవినింగ్ వచ్చేస్తావా?
ఈవినింగ్, ఎర్లీ మార్నింగ్ సార్.
వెరీ గుడ్, ఓకే, రైట్.
ఎస్ సార్.
ఏమమ్మా ప్రాబ్లము? అవునా మేడం?
లేదు సార్, ప్రాబ్లం ఇది ఓరియంట్ అవుతుందని రిమూవ్ చేస్తారు.
ఓకే.
మేడం, యూట్యూబ్ లింక్ ఎవరు చూస్తున్నారు మేడం? యూట్యూబ్ లో కూడా టైం టు టైం ఎంతమంది వ్యూవర్స్ ఉన్నారో చూడాలి మేడం.
Sir, good morning, sir.
Good morning, sir.
Very good morning, sir.
Nice to see you here. Thank you, sir.
Yeah. Good morning, sir.
Good morning, sir. How are you?
Yes, sir.
Fine,
Good,
sir.
sir. Good. Yes, sir. We are good, sir.
Many more happy returns of the day, sir.
Thank you. Thank you.
Sir, many more happy returns of the day, sir.
So, yes, on my birthday, my first thing is this talk. So, I'm glad to be here. Yes, nice.
Thank you very much, sir, for
Thank
accepting
you
our
so much, sir.
request.
So, tonight, tomorrow I'll be reaching Amravati. Yeah.
Okay.
So, Abhijit has also joined, or he'll join later.
Yes, sir. Abhijit joined.
Yeah, yes.
Abhijit, sir. Good morning, sir. Abhijit, sir.
Good morning, sir. Good morning.
Good morning.
Good morning, sir. Subramaniam, sir. Good morning.
Yes. So, are you part of the quantum AI team that is there in Hyderabad now?
Yes, sir. I'm part of quantum team in CDAC Hyderabad, sir. So
Okay.
two scientists are working in CDAC Hyderabad. One is working on quantum accelerator, and other is working on quantum machine learning. I'm in both of them, sir, mostly. But my major work is on quantum accelerator.
Very nice, very nice. Because I think Hyderabad is the lead for the quantum machine learning, I think.
Yes, they are doing, sir. They are doing it.
Hmm.
Thank you, sir.
Yes, sir. Our registrar, sir, has joined, sir, and also the convener, ma'am. So everyone has joined.
Sir, good morning, sir.
Good morning, sir. Nice to see you on a Sunday also, working hard.
Sir, happy birthday, sir. Many more happy
Thank
returns
you,
of the day.
sir. Thank you, thank you.
So we are very fortunate to have you here on this day, on the occasion of your birthday. I
Thank
told to Professor Madhumurthy is also, sir, our APSA chairman, about your lectures, and sir is busy with other engagements. Sir. So
I get it. I understand. Yes. Thank you so much. Yeah. So, sir, this is a great initiative that you are starting. It's good to see all the focus and energy around quantum. So I'm sure it will benefit all the students and faculty and everybody. And I think Andhra is where a lot of the action today is. So I'm hoping that by next year we have a lot of great research papers, solutions, everything coming out of Andhra Pradesh, and especially your university.
Thank you, sir. Thank you, sir.
yeah.
Thank you, sir. Good morning, all. Just as life begins a single cell whose complexity enables growth and adaptation, quantum technology starts from a qubit, the smallest unit of quantum information, upon which we are building complex systems to harness advanced technologies for the benefit of humankind as we change from classical systems to quantum systems. As part of the important and challenging journey, in alignment with Quantum Amravati Quantum Valley Mission and National Quantum Mission, Rajiv Gandhi University of Knowledge Technologies, Andhra Pradesh, has initiated several programs to advance research, education, and innovation in quantum technologies. The Quantum Lecture Series, one such an initiative from Rgukt AP. It is my privilege to extend a warm invitation to you for the inaugural session of the Quantum Lecture Series organized by Rajiv Gandhi University of Knowledge Technologies, Nuzvid Campus, Andhra Pradesh. I am Dr. Pavani, convener of Quantum Lecture Series, Rgukt AP, and head of the department, Mechanical Engineering, Rgukt AP. I sincerely I sincerely thank the Rgukt Nuzvid administration for initiating the Quantum Lecture Series and for entrusting me with the responsibility to take the initiative forward. I now have the honor of inviting Professor R.S. Amrendra Kumar Sir, Registrar of Rgukt AP, for today's inaugural session.
Yeah, thank you, madam. A very good morning to our chief guest for today's inauguration session, Dr. L. Subramanian, IBM Quantum India Lead, and to all my dear colleagues and participants of the inaugural session of the Rgukt Quantum Lecture Series. Inspired by the visionary leadership of our Honorable Chief Minister of Andhra Pradesh, Sri Nara Chandrababu Naidu Garu, and Deputy Chief Minister, Sri Konindal Pawan Kalyan Garu, and under the esteemed guidance of the Minister of HRD, Sri Nara Lokesh Garu, and in alignment with the Amravati Quantum Valley, Rgukt Andhra Pradesh has taken several initiations in the field of quantum technologies. These initiatives have been consistently supported and guided by our Honorable Chancellor and Chairman APSE, Professor Madhumurthy Garu, and our respected Vice Chancellor, M. Vijay Kumar Garu. So finally, I would like to extend my heartfelt thanks to Dr. L. Rgukt Subramanian Garu, IBM India Quantum Lead and Chairman of the Quantum Committee Rgukt AP for his invaluable support and guidance. Sir, we sincerely thank our Honorable Prime Minister Sri Narendra Modi Garu as well for setting ambitious target to advance India's leadership in quantum technologies through the National Quantum Mission and the National Education Policy. Some of the key developments happening at Rgukt AP towards quantum technology are as follows. Considering the geographical advantage and expertise of faculty, each of the 4 campuses of Rgukt AP is being working on setting up centers of excellence in the following areas: Rgukt Nuzvid campus, quantum computing; Rgukt RK Valley campus, quantum communication; Rgukt Ongole campus, quantum materials and devices; Rgukt Rgukt campus, quantum sensing. Sir, these 4 institutes are located across the state in different parts of the state. Rgukt AP is offering minor degree program in quantum technologies for about 500 students from the academic year 25-26 to the current BTech third year and BTech second year students. Considering the significant advantage and potential employment, Rgukt AP is also planning to offer certification program in quantum technologies for the current BTech fourth year students to meet the immediate demand of the Amravati Quantum Valley. Rgukt AP Rgukt campus got selected for hosting the prestigious IBM Quiz-Kit Fall Fest 2025 under the sponsored category. We are happy to announce that Rgukt AP is in the top 55 selected institute across the globe for hosting this event. Rgukt AP is planning to conduct this IBM Quiz-Kit Fall Fest 2025 as a historic and one of the biggest events in India. So about 30 faculty members, not to talk. About 30 faculty members from the Rgukt AP are undergoing faculty development program on QT00 and QT01 being organized by APSE collaboration with MNIT Jaipur. Rgukt AP 4 campuses submitted proposal for quantum UG labs to the DST and are awaiting for a positive response. 8 teams from Rgukt AP got selected for semi-finals of Amravati Quantum Valley Hackathon program. About 100 plus teams participated in the internal hackathon and the evaluations were done with the distinguished jury panel from academic industry, that is from TCS, BQP, CDAC, IISc Bangalore, MNIT Jaipur, etc. Rgukt AP is working on hosting Rgukt Global Startup Hackathon, and quantum technology is one of the prime theme in this event. Initiations of the Quantum Lecture Series. So with the above initiatives, the university would like to reaffirm the strong intent, commitment and dedication in realizing the vision of the Swarnandhra 2047 and Viksit Bharat 2047. Now on today's initiative, the objective of this Quantum Lecture Series is to ignite curiosity, nurture talent and inspire students and faculty to explore the fascinating world of quantum technologies while also advancing research and innovation. By providing a platform for interaction with the experts and thought leaders The series aims to foster collaborations, bridge academic and industry, and equip participants with the insight needed to address complex scientific and technology challenges, thereby contributing India's leadership in this transformative field. So with this, I would like to convey my best wishes to organizing team of Rgukt Quantum Lecture Series. Sir, we are planning to organize this lecture series one in every week. Like that, in this total in this year, we're planning to organize minimum 30 lectures. It may go up to 50 also. Sir. Sir, thank you, sir. Thank you for accepting our invitation. And over to you, sir. Please.
So we have small AV from Rgukt campus. So we watch the AV on, sir. Please.
Sorry, ma'am, you have a what?
AV, sir. AV.
Oh, AV. Okay. There's no sound. Is there a sound?
Ma'am, can you check for volume? Pavani, madam?
Beat the chain, Amma.
No, madam, not audible.
Yes, sir. Sorry for the inconvenience, sir. So I request the today's chief guest, Dr. L. Subramanian, sir. Sir, please start the session, sir.
Okay, sure. So we will see that AV later. Maybe you can try challenge.
Yes. Okay.
Okay, so it's really an honor for me to be with you all, and actually within a very short period, within I think 2 or 3 months, you have made so much progress. So I want to congratulate each one of you for the great work that you have done, to reach up to this point. For I work with universities around the world, okay, and to reach this level, it usually takes a year, sometimes even more than a year, okay. So you've done an amazing job. Please keep up your speed, your momentum, and the focus, because you are on your path to be the best. So please keep going like this, and you will get to be among the best universities in the world. So I'm really thankful to be associated with you, and whatever
Thank you, sir. Thank you very much.
So whatever work you're doing, please feel free at any time to seek any help that you need. And I'll try my best to connect you with the right people. Or if I can help directly, I will try and do that also. So I'm very happy to be associated with your team here. Thank you so much. So today I'm going to give you a very high level overview of where is quantum computing headed, and where is India, and what are we as a nation doing, and where are you in this, all of this? How can you help? I'm just sharing my slides. Okay, so this decade, for various reasons, just 3 days back, the Prime Minister Shri Narendra Modi was at our IBM stall. There was a conference called Semicon 2025, and he visited the IBM stall. So at the IBM stall, just like we had installed at Amravati the the quantum computer replica, the golden colored system, the same way we had installed it in our stall here in Delhi. And when the Prime Minister came, the first question he asked was, "This is beautiful. How much of this is made in India?" That was his first question. Okay. And our answer was that, "Sir, right now we are on a path to making some of these components, but still nothing is made in India." Okay. So his answer was that Indian students are the best. You try and give it to them and they will make it better than anybody else in the world. So that's what he said. Okay. And that is true also. That's very much true, because even that system which is sitting here, which was sitting here in Delhi, and the Prime Minister saw it, a lot of those components are getting made by Indians in the US. They could be students of the Rajiv Gandhi University here in Andhra Pradesh. Some of those students could be there in New York making these components. So now, what we really want is for our students, yes, some of them can go to US and all, but we want many of them to stay back and make these components in India. That's what we really want. And that's what your university is enabling through the Kiskit Fall series, through the hackathon, through series like these, where you are hosting talks. What you really want is to have all these interactions become very active and very productive, so that you are all, on your path to making some of these components and making some of the software and algorithms here in India. So that's what you really have to aim for. And I really want that by next year, this time, there is something, at least 1, 2, 3, 4, 5, some items which you in your university, it can be in hardware, it can be in software, but you and your students need to be making these things here in India, out of your university. Okay, so by next year, that has to be our target. And with the Chief Minister's support, we will get there. In fact, on 9th, there is a meeting with the CM sir, where we are exactly discussing this as to how universities in Andhra Pradesh can start making, whether it is software products or hardware products, but made in Andhra Pradesh. That's the goal. And for that, it's beautiful that you have set up 4 hubs. I think you should name these hubs according, by some great scientists from India or people like that. It'll be a very nice initiative. It is something which is giving a lot of hope to everyone to see your university taking this lead and setting up all these hubs, labs, having hackathons and meetings like these. I think this is a crucial piece. You're taking the right steps. And as I said, across the world, I'm seeing, universities in Korea, Japan, US, Europe, and the speed with which you are working, within 2 or 3 months, you have a course ready. Students are taking that course. 500 students. I don't know of any other university where there are 500 students taking quantum technology course. Honestly, I don't know of any university in the world. Yes, in Japan, Korea, there are some universities where there are tens of students, but not 500. So congratulations, this is a great, great thing. And we are truly on our way to this India's leap forward, the quantum decade, through efforts like yours. Now, quantum technologies, so on our computer, when we write a program, we typically write it in what is called a higher level language. A higher level language, things like C, Java, Python, they're all English-like languages. You write your program using loops like for loop, while loop, and then you are writing functions. All of them are written in almost English. So they are called higher level language. Okay. But your processor at the back does not understand this higher level language. So in between there is something called a compiler. And that compiler, what that compiler does is it converts your higher level language into machine language. And in the case of your mobile phone, laptop, your classical computers, this machine language is string of bits, because bits are the fundamental unit of computation on a classical computer. Now on a quantum computer, you already know this, of course, because you are already conducting this hackathon. The higher level language is the same. It is the same Python. Okay, it's called Qiskit, but it is basically Python. Okay, Python, the same higher level language as you write on your classical computer, same one, Python, but the compiler now, or the transpiler as it is called, now compiles this higher level language into a language where the processor now is made out of qubits, because qubits are the fundamental unit of information on a quantum computer. So while the front end or the higher level language remains the same, the back end changes, the qubit bit. So now for the first time in the history of computation, there are two types of computers. One is your classical computer, your mobile phone, your laptop, the best supercomputers. They are all using bits for as their fundamental unit of computation. The compiler compiles your higher level language into a string of zeros and ones that your processor understands. But now there is a new kind of computer called the quantum computer, which is not an extension of the classical computer. It's a new kind of computer because it's using qubits. Up to now, every type of computer that you had used bits. This computer is entirely new technology. It does not use bits at all, right? And that's the difference. Now this is Summit, used to be the most powerful supercomputer, but there are things that Summit also cannot do. Things like computing with caffeine. For example, if you wanted to model the caffeine molecule, which is structured like this, and it's one of the small molecules of nature, if you were to try and model this molecule on a classical computer made of bits, you would require 10 to the power 48 bits. If you put together all the bits in the world today, you would still not reach 10 to the power 19. So 10 to the power 48, forget it. Can't get there. Okay. So hence, we will never build a supercomputer this big, which contains 10% of the total number of atoms on Earth. 10 to the power 48, which is 10% of the total number of atoms present on Earth. We're not going to build a computer this big. And that's where quantum computers come in. With just 160 qubits, your quantum computer can solve this molecular simulation for a fraction of a second. How the molecules are placed, where are the electrons, where are the neutrons, where is, how are the two atoms in that, configured. All of this can be done with 160 qubits, but it cannot be done even with the best supercomputer available today, you cannot do this on the best supercomputer. And you cannot do it in the future either, because supercomputers are unlikely to have 10 to the power 48 bits ever. Okay. So that's one problem, molecular simulation. The second problem is that of factorization of large numbers, large integers. And Shor's algorithm, which I'm sure all of you would have heard about. Today, our encryption, whether it is our passwords, whether it is this talk, the call, the Zoom calls or the Google Meet calls, they are all encrypted. So even if somebody gets this signal outside, they will just see the signals, but they will not be able to decrypt it. The reason for that is that the keys are large numbers and large prime numbers which cannot be factorized. So what does that mean? Prime factors of 15, 3 into 5. Prime factors of 100, 5 into 2 into 5 into 2. These are the prime factors. But a prime factor of a large 2048 bit integer, it takes close to 8 billion B with a B, billion with a B years to decrypt that. And that's why we take two large prime numbers. I take a large prime number, you take a large prime number. We multiply and use that as our key today. Okay, because we know that no supercomputer can break that. But Shor's algorithm in 1994 showed that you can actually do this decryption. You can break RSA encryption, which is based on large prime numbers. And hence, since then, we have been looking for what is called quantum safe algorithms or quantum safe encryption. And that, so there are already algorithms there. But the second point I wanted to make, the first one was you cannot simulate molecules using classical computers. But with 160 qubits, you can. You cannot factorize large numbers efficiently on the best supercomputer. But if you had a quantum computer, you can factorize. Third one is learning. What is AI? AI is about taking a lot of examples and learning from that. We do that all the time. As children, we were taught animals, cat, dog, cow. And as children, how many cats did we have to see? Maybe one, maybe two, maybe three. After 1, 2, 3 cats, we would say, cat, mama cat, papa cat. We did not need too many examples. But today's AI, how many cats does AI need to see? It needs to see thousands of cats, because otherwise the cat will, the AI will confuse cat with lion. It will even confuse it with the piece of cake if it is shaped like a cat. So all of these reasons make it very difficult for AI, and AI today needs lots and lots of examples. Same cat that the baby recognizes, same cat the AI also recognizes, but because of the way the data is represented and inferred, it is a challenge. The cat that the AI is inferring is very complex for it. It's not able to infer it properly. It is getting confused between all kinds of animals and even cake, which looks like a cat. So now quantum brings that AI processing also closer to human. Maybe not 2 cats, but a few cats, but definitely not thousands of cats. So I gave you 3 examples now. One is molecular simulation, much more efficient on a quantum computer. The second example I gave was factorization. much more efficient on a quantum computer. Exponential, 8 billion years versus 8 hours. Exponential, okay, that's the increase that you are getting as a result of using a quantum algorithm. The third one I gave is learning. AI is also much more efficient. But remember, we started here saying that your higher level language remains the same. Qiskit or Python is your higher level language. What is changing is how the processor is looking at the data, how it is inferring from that data, how it is, projecting that data into different mathematical spaces. That's the difference. So the difference for all of you is now that, you will still write using the same Python language, but you're going to think differently because you are now going to see how am I going to use quantum mechanical properties which can run on this quantum processor or the qubit and solve my problems. Okay, and just the way, for example, that Shor did Shor's algorithm or Grover did Grover's algorithm. So the same way, you now have to come up with new algorithms to solve new problems, and that's what you are already doing as part of your hackathon. In your hackathon, you are now looking for solutions to other real life problems. That's what you are doing, and that's what your students and all of you need to do. And by next year, that's what I was telling you in the beginning, by next year you need to be in a position that you are among the best in the world, where you are able to come up with new ideas and new algorithms that will help people solve a wider range of problems, whether it is in learning, whether it is in factorization, because more efficient algorithms can also be found compared to Shor's, or whether it is in molecular simulation. But at the same time, I'll not go here much, but the challenge for classical computers is that they use zeros and ones. And so they are not able to represent the cat properly. They are not able to represent molecules properly. They are not able to do factorization properly. Whereas quantum computers use what are called qubits, and these qubits have these special properties of superposition, entanglement, interference, and these properties make these qubits do special things. So for example, superposition allows us to give the qubit multiple states simultaneously, both 0 and 1 simultaneously at the same time. And what does that mean? That means, for example, if I have a maze and every path in the maze, one path is 0, 0, 0, 0, 0, the next path is 0, 0, 0, 0, 0, 1, the next path is 0, 1, 0, 0, 0, 0, different combinations of bits. On a classical computer, I have to try each one of these sequentially, one by one, one by one. First I try 0, 0, 0, 0, 0. Does it take me out of the maze? Is that the correct path? No, maybe not. Then I try the next one. But on a quantum computer, what I do is, because qubits can be simultaneously 0 and 1, I try out all the paths simultaneously, and using something called interference, where the likelihoods are amplified, the correct likelihoods are amplified and the wrong likelihoods are attenuated. That allows me in one shot, tuck, like that, to find that path. Something on a classical computer I had to try one by one, one by one. Here in one shot I do it because of superposition, entanglement and interference. Okay. So that's the beauty of quantum computers, but it's only good for certain problems. Okay. So if you wanted to do multiplication is much faster on your classical computer. Okay. So in future, you are going to have both classical and quantum computers working together. You are not going to have only quantum, or you are not going to have only classical. You are going to have CPU, GPU, and QPU working together. Already your CPUs are on your mobile phone, on your laptop. CPUs are there. Very few laptops have GPUs, but usually the GPUs are sitting in the cloud. In the cloud center, the data center, your GPU farms, where all these GPUs are lying there in racks. Those are your GPUs, okay? And also now you can access QPUs on the cloud. Okay, so all of you can access QPUs on the cloud. So in the hackathon, I hope all the students are learning to use QPUs also, because that's the purpose of the hackathon. It is to make sure your students know how to use CPU, which they already know because they use a mobile phone, they use a laptop already. Some of them might also be using GPUs, but now through the hackathon, you want to make sure that all your students are using QPUs also. Okay, QPUs are freely accessible over the cloud. IBM gives free access to every student, every faculty for 10 minutes for a month. Now, if you are able to finish that 10 minutes, please come to us. We will give you more. But if you finish your 10 minutes, each one of you finishes each of your 10 minutes, you're a great person. Okay. That means you are among the best in the world already. You are able to use, because most programs, you run it, it will run in a fraction of a second on a quantum computer. So to finish your 10 minutes, you really have to be a great guy or a girl, great person who can utilize your 10 minutes of time, free time. Okay. So please make sure all your students in the hackathon, they are using QPUs. That is the most important learning from your hackathon that you have to give to students. If they are only using CPU or only using GPU, they are not doing the right thing. They have to use QPUs, because that's how they will get an experience of the quantum computers, and that's what the hackathon's goal is. The goal of the hackathon is to make every student create an account for themselves and use a quantum computer for themselves. Okay, that's what they have to do. Now you all know about Moore's law. Moore's law states that classical computers double in power every 18 months to 2 years. So almost every 2 years, you are getting a new mobile phone, a new laptop. Why? Because the camera is much better, the apps run much faster, the more complex programs can be run on them. It's all because of Moore's law. Moore's law has, for several decades now, has been doubling the performance of our classical computers. Quantum computers are also equally very powerful, and they are also growing exponentially. 2016, 5 qubits, 2024, 156 qubits. By 2033, there will be 1 lakh qubits. Okay. So which means, quantum computers, just like Moore's law, there is a law for quantum also, where they are doubling in their performance every year, in fact, at this point of time. Okay. So this is exciting times, very exciting, which means that the quantum computer you have today will very quickly become redundant, and you will be able to do much more powerful things next year. The quantum computer next year will become redundant very soon, and you will be able to do even more powerful things the following year. Okay. So each one of you needs to keep up the pace. Start using these quantum computers. As I said, please access the QPUs on the cloud. Okay. That's when you can say you are doing real quantum computing. Once you have accessed the QPUs and run your programs on them. Until then, you are not doing quantum computing. Okay. So there are some good milestones now. 2027 there'll be 156 qubits, 10,000 gates. The following year 15,000 gates. In 2029 there will be error corrected gates, and by 2033 1 billion gates. 1 billion. Okay, right now we are at 5,000 gates in the year 2025. 5,000 gates. Now imagine the kind of growth that is going to happen, the kind of programs you will be able to run by 2033 with 2,000 qubits, error corrected qubits, and 1 billion gates. Okay, which means you can start running really large programs by 2023. But those who are in the first year now, 2025, by the time they graduate, error corrected qubits with 100 million gates will also be available. So just think about the growth here. Just think about it. 2025, 156 qubit, 5,000 gates, and look at the exponential growth which is going to happen. 100 million gates within 4 years, 1 billion gates within 8 years. So the growth of quantum computers is happening very, 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 very quickly. And it's great that you have started out on this path of teaching to your students, of figuring out how you are going to utilize this extreme power that the quantum computers bring to you. That's very, very crucial. Okay, now another big milestone is the quantum advantage milestone we will reach next year. 2026 is the likely date for quantum advantage. What is quantum advantage? It is the day when quantum computers on one business task, any task that you are aware of, starts doing much better on a quantum computer compared to a classical computer. And the hackathon that you are giving is precisely for this. It is to make your students reach quantum advantage. Basically, be able to do things much better on a quantum computer, either in terms of speed, in terms of cost, in terms of efficiency. In any of these terms, your quantum computer should, your algorithm on the quantum computer should perform much better compared to anything it does on a classical computer. The day it does that, we say you have achieved quantum advantage. Now, IBM expects that this quantum advantage will be reached by 2026. We are at almost the second half of 2025. 2026 is not far. And where is quantum advantage going to come out of? Today, the talent is sitting in India, quantum talent. We see it on our IBM computers. Which country uses the maximum quantum computers on the cloud? India. US, India, US, India. So today, India has the largest talent pool in quantum technologies anywhere in the world. Okay, this is a McKinsey report. They said that European Union has more people compared to India, but remember, European Union is a collection of multiple countries. Tens of countries put together is European Union. You take any single country, they fall behind us. Okay, so India is where the talent is, and hence India is where quantum advantage should come out of. And hence your hackathon is extremely important, because it is teaching your students how to use quantum computers. It is teaching them how to write algorithms. It is teaching them that how once they solve these problems, they can achieve quantum advantage. So in your hackathon, your students should not only implement these algorithms on quantum computers, but they should also implement them on classical computers and show that what they are doing on the quantum computer Today maybe it's not better, but they're improving. They're getting better, and they are likely to achieve quantum advantage. Okay. The goal of the hackathon is this. The goal of the National Quantum Mission's algorithm call was this: to achieve quantum advantage, and to achieve quantum advantage from where? From India. Why? Because this is where the talent is. The talent is in India, and if somebody else achieves quantum advantage with lesser talent than us, then what? It shows that we did not use our talent properly. And how do we use our talent properly? Through efforts like you are doing, by teaching students, by making sure that they are using quantum computers, by making sure that they are writing algorithms, comparing those with classical computers, and always trying to improve the quantum results. And what we have observed is that when somebody tries to do that, their classical results also start improving. So it's like this: you keep improving on both the fronts, and that's what your hackathon is all about. And that's what the Kiskit Fall Fest is all about. It is to ensure that your students start working at the cutting edge of technology better than anybody else in the world. Okay, that's your goal now. So to achieve this, of course, the government of India, through the Department of Science and Technology National Quantum Mission, has approved this 6,000 crore budget, and that budget is already going now. It is going to all these universities across India. For your students, every one of these institutions is now hiring faculty, hiring SRF, JRF, Junior Research Fellow, SRF. They are all opening MTech programs, BTech programs, but you have gotten ahead of them. You opened your quantum technology program before many of these institutions. So remember, that's why I said in 3 months what you have achieved is more than many institutions, not only in India, across the world have not achieved. These 43 institutions, yes, I know ISC Bangalore has a MTech program in quantum technologies, IIT Madras has, ISER Pune has, but what about the rest? They have nothing. You have it. So this is amazing what you are doing. Please be proud of what you are achieving here and keep focusing and working hard. Okay. You are already ahead of many of these institutions. Okay. So keep doing that, keep working hard. Make sure your students and your faculty are working at the cutting edge of technology. The second thing, the National Quantum Mission has announced these startups. They had a startup call, 8 startups. Then in the first round, 8 startups applied, and 100 plus startups applied, and 8 of them were selected. The government is again giving between 1 crore to 25 crores to these startups. For the first time in the history of India, government is giving such large sums of money to people. Okay, it didn't happen before. For the first time, so much money is being given to startups, and I would again urge some of you, all of you might not want to open startups, some of you might want to do what you are doing, but please, some of you think about what are those startups you can start. What problems can you solve using quantum computers? And the hackathon is an excellent place for that. If you get some good results in your hackathon, start a startup with that idea. Go and start a startup. It will be supported by the National Quantum Mission. The third thing, of course, courses were started in quantum technologies, but this one I don't need to tell you because you were ahead. Other institutions, most of them have not even started. You have started already. You have enrolled 500 students, which is amazing. Okay. So there are multiple new results which are coming out from across the world. I'll not go into them, but there are, every industry today is exploring how they can use quantum computers. Banking, they are looking at how can they do fraud monitoring, how can they do portfolio optimization. The other day we were talking with Maharashtra government. Maharashtra government has this, I mean, the Indian government is giving money to um, state governments under a scheme called BharatNet. BharatNet. In BharatNet, the goal is to take fiber, the best fiber, to all the villages, all the gram panchayats, okay, in the state. Now, there is a money allocated for it. Let us say 10 crore, 20, 100 crore, whatever, X crores. You want to reach all the gram panchayats. What is the best route? It's an optimization problem. Can you solve it? That is a beautiful problem for you to solve on a classical computer and quantum also. And the day you have a good solution, take it to Chief Minister sir and say, look, Andhra also has BharatNet project. You can type BharatNet, BHARATNET, okay, and it will show you. Andhra also has allocated some 1,000 plus crores for this. If you have a solution on how to lay fiber in an efficient manner so that it goes to all the gram panchayats for a given budget, you have a beautiful solution which every state in India will want. The Prime Minister will call you and they will felicitate you. Okay. So these are all the problems, and this is where quantum advantage will be reached. It could be in BharatNet problem, it could be in fraud, it could be in efficient drug design. All of these are projects and problems people are trying to solve. And in the hackathon, I know you have, I think, 10 problems that you have selected, and I'm sure it fits into some of these categories here. So these are the things that you need to be solving today. Your students need to be solving, and they need to be solving it on a real quantum computer, not on anything else, but on a real quantum computer. Okay, so please do that. Okay, now, so 3 classes of problems. Remember I told you about caffeine, that is simulating nature. Remember I told you about AI and about factorization, that is mathematics and processing data with complex structure. Remember I told you about this BharatNet problem, it is optimization, search and optimization. Okay, I told you about the maze problem also. So each one of these categories of problems are what quantum computers are good at, and they are now being used across different, areas. That's what is being done today. Okay, so this is what we are doing, and these are the things which will allow us to solve some of the important problems. Okay, so that's the goal here. I also want to tell you about the the hardware aspect of the things. Okay, so today your mobile phone, your laptop, any of that, whether it is software or hardware, 5 countries control the supply chain: China, US, Taiwan, South Korea, Japan. India is not there. Part of the supply chain, laptop or for there. India does not control many of the electronic components. India does not. Okay, but what do we want in the future in quantum? In quantum, we want that India should be controlling the supply chain for whether it is cryogenic components, all of these we want that India, whether it is cryo, should be controlling. And that's where the labs that you mentioned you are setting up are very crucial, because they will train our students to build some of these components, to see how you can use some of these components. That is the goal. Okay, so even in hardware, because you are opening those labs, it is crucial, and build things that will enable our students and faculty and everyone to start using quantum computers to build things. They should be able to eventually build some components, build, assemble quantum computers, check out what kind of hardware is in there, open them up, put them back together. All of those things we should be able to do out of India. So please, as you've begun your journey, it's a great thing. All of you please get going times, and feel free to reach out to me anytime for whatever help you need, anything you want to do. All of these things are crucial for all of us. Okay, we want you to succeed, and whatever you need to succeed, we will try our best to give that to you, so that you are actually succeeding. Okay, so I will stop here. So thank you so much. It was such a pleasure to talk to you. I'll be happy to answer any questions that you might have.
Sir, thank you very much, sir, for your time on this day. Today is sir's birthday, actually. Yeah.
Thank you.
Yes, like anybody would like to ask any queries, please feel free to ask, sir. Yes, please.
Yeah, good morning, sir, and happy birthday to you.
Thank you.
I have a
Thank you.
question.
So nice of you. Thank you.
One of the application you mentioned in learning. So,
Yes, sir.
you mentioned that the classical computer needs thousands of samples to train the model to recognize an object. Because if samples are very few, it may simply overfit. So coming to quantum computer, or if we design the learning model with quantum, can it learn with few examples only?
Yes, sir. Yes, sir. So we have done some experiments. Not only us, many people in the world have done experiments. Okay, where we are observing that quantum, because the data representation happens in a Hilbert space, in a mathematical space, and we are finding that that's much more efficient compared to how the data gets represented in a, in a classical world. And these are experiments, sir, that you should actually do yourself also in your lab. Okay, run, let's say, a classification problem on a classical computer using a classical algorithm like SVD or whatever you like, and also implement the quantum version of it, quantum SVD, quantum whatever, ML methods. Okay, and we actually observe that you are able to learn with fewer examples using the quantum algorithms.
Okay, sir. Thank you.
Yes. Sir, ready? Sir, we have a small AV, sir. Like, I would like to play that one for how many minutes?
Yes, sir. Yes, sir. Let's do it. Yeah.
Let's play. Let's share.
Let's see.
Stop this.
Sir, thank you so much. I don't know what to say. Actually, I don't deserve any of this. Okay, honestly, I am not some, but I'm so
Okay.
thankful to you, and it's a very special birthday gift for me. Thank you so much, and I really appreciate the efforts you are putting to make quantum computing big for India to lead. Okay, that's what we really have to do. So thank you. I'm very touched. I have no words to say here. Thank you so much, sir.
Yeah. Sham,
Yes, sir. Yes, sir.
yeah, please propose, conclude the session and propose vote of thanks.
Sir, Subramaniam, sir. So thank you very much, sir. So for supporting us. So from the last, it is our privilege, sir, to have you in our quantum communication committee also. As soon as we have requested, you have accepted us, and so from there onwards, we are taking this forward under your guidance. And also regarding the Kiskit Fall Fest also, so you are the one who has directed the Kiskit Fall Fest to me, and we have immediately taken up, sir. So thank you very much. Sir, I take advantage of we have spoken about this for the last 6 months. Nikhil, are you online?
Yes, sir, I'm online.
Yeah, Nikhil, please, Nikhil.
Okay, sir. Respected chief guests, distinguished dignitaries, faculty members, and dear participants, It is indeed my privilege to deliver the vote of thanks for this memorable inaugural session of the Quantum Lecture Series. First and foremost, I express my deep gratitude to Dr. L. Venkat Subramaniam Garu, IBM Quantum India lead, for his inspiring lecture. Many happy returns of the day, dear sir. On a personal note, sir, I must share that your book had a transformative impact on me. Later, when I had the honor of meeting you in Delhi and receiving your signature on that very book, it became a lifelong treasure. The interaction gave me the conviction to start the Quantum Technologies Club across all four campuses of RGKT. The book is still with me, sir. I also request my juniors and all the students to read this book. It's a wonderful book. It is with your constant guidance and encouragement that RGKT has now been selected to host the IBM Qiskit Fall Fest 2025, a global recognition for our student community. We are truly grateful, sir, and we humbly request you to extend your continued support as we move forward. In fact, we would be most delighted to host you offline at RGKT in the near future. Your words today align perfectly with the broader national vision, the National Quantum Mission, and our dream of creating an Amaravati Quantum Valley, which can position Andhra Pradesh and India as front runners in the quantum revolution. I also extend heartfelt thanks to our RGKT leadership, dignitaries, and faculty members whose encouragement has made today's event possible. A special note of appreciation goes to Dr. U. Pavni Garu, the convener, and the organizing committee for their dedicated efforts. I extend heartfelt appreciation to Professor Madhumurthy Garu, Honorable Chancellor of RJKT and Chairman of APSI, whose visionary leadership has been instrumental in shaping higher education and guiding RJKT. I sincerely thank Professor S. Amrendra Kumar Chandra Garu, Registrar of RJKT AP and Director of RJKT Nuzvid, for his constant encouragement and supporting in making academic initiatives like this possible. I also wish to acknowledge Sri Nara Chandrababu Naidu Garu, Chief Minister of Andhra Pradesh, whose visionary leadership continues support to shape our state's future. Under his guidance, initiatives like Quantum Valley and Amravati are taking tangible form. His commitment to tech-driven education reforms, emphasizing quantum computing and future-ready infrastructure, aligns perfectly with our aspirations. Lastly, I thank all the enthusiastic participants for joining us today. With your energy and with leaders like Venkat sir guiding us, I'm confident this quantum lectures will open new doors of learning and collaboration. Once again, thank you all.
Yeah, thank you so much. And I must say, each one of you, I've maybe met you one time or two times, and sometimes online only. But what you have achieved by yourself is amazing. Please, you have to feel proud of what you have already achieved and keep working on top of it, because as I told you, I keep repeating it. There are very few colleges around the world which have done what you did in so few months. Okay, nobody has done it. Okay, honestly. And so, which means you are very special. Okay, I want to keep telling you that you are very special people who have done something in such a focused manner. Please continue that. It's a great beginning, and I'm very happy that I got an opportunity through God to get connected with all of you. So, and thank you for that video. It's amazing. I never expected, and I don't think I deserve any of this, but thank you so much. Thank you.
Thank you, sir.
Thank
Bye.
you, sir.
Okay.
Thank you, sir. Thank you, sir.
Thank you. Bye bye.
Thank you, sir. Have a nice day.
Thank you. Bye.
Thank you, sir.
Thank you very much, sir.
Hello.
Madam, are you there? Hello?
Hello, sir. I'm Abhijit
Hello,
Singh.
sir. Hello.
Yeah, yeah, yeah. Nice to meet you,
Welcome,
sir.
sir.
Yeah.
Yeah, sir. I'm waiting for convener, Dr. U Pavani.
Sure, sure, sir. We'll start by 10:30, sir. Are the students watching it live in YouTube or?
Yes, sir. Here only as it is limited to 100, so we connected very heads and officials through Meet,
Yeah.
and others are watching through YouTube, sir.
Sure, sure, fine. Is my voice audible or do I need to use
Yes, sir.
any?
Audible, audible.
Yeah, is it clear, right? So I
Yeah,
can
yes, sir. It's clear.
continue. Okay, sir. Thank you. We'll start by 10:30 then if everyone is ready.
Okay, sir. Okay, sir. 10
Yeah.
minutes.
Thank you.
Welcome back for the second session, Quantum Lecture Series 2. For the second session, we have guests from our alumni from Rgukt Basra campus. And he is working from CDAC, Hyderabad. And I request Nikita to introduce the guest for the today's session.
Sir, it's an honor for me to read about you. So, Abhijit Tej Vadeboina began his academic journey at Pratibha Vidyaniketan High School, completing his schooling in 2014. He then pursued pre-university at Rgukt Basra from 2014 to 2016, followed by a BTech in Electrical, Electronics and Communications Engineering at Indian Institute of Aeronautical Engineering in 2017 to 2021. To further specialize, he completed his MTech in Quantum Technology at the Indian Institute of Space Science and Technology from 2022 to 2024. Alongside his studies, he gained industry exposure through internships, first at Smart Bridge, Hyderabad in 2019, where he developed an IoT-based smart waste management system, and later at Tata Consultancy Services, Research and Innovation Labs, Bengaluru in 2023 to 2024, where he worked on quantum communications and networking protocols. Currently, he is working as a knowledge associate at CDAC, Hyderabad, focusing on quantum computing and quantum algorithm. It makes us really proud to have you as our alumna, and we are looking forward to hearing your thoughts.
Thank you very much for the wonderful introduction. Am I audible and am I clear?
Yes, Abhijit. Please go ahead.
Thank you. Respected Amarendra Kumar sir, Professor Amarendra Kumar, Registered Rgukt AP and Director Rgukt Nuzvid, and respected HOD Mechanical ma'am, thank you for inviting me for this lecture. It is a privilege for me to come back here and contribute to Rgukt again. I share very good moments with Rgukt. My whole thought process, my whole understanding has developed in the Rgukt days itself. So it is actually very good to come back and contribute to you, and also congratulations for all the selected candidates for selecting into semi-finals of Amaravati Quantum Valley Hackathon. I had the privilege of being a jury member for RGKT RK Valley, and the students were excellent. They're awesome. That is the that is the very good product of RGKT. The people here, the students here are they very work hard. Like I have seen people working hard day and night rigorously. So this honest and working hard students will definitely go into the future, and I'm expecting a huge success for them. And also congratulations for all the RGKT 4 campuses for taking this initiative for developing quantum technology, like one technology in one campus. As I have heard you saying, quantum computation in one of the campus, communication in one campus, devices in one campus. So this all belongs to quantum technology domain as a whole, and I think RGKT is very quick to grab, and I appreciate RGKT whole campuses of all AP for training their students into the minor of this course. Really having 500 to 600 students within next 2 to 3 years who will become technocrats in quantum technology is a really good privilege. Like people need, we need technocrats in quantum because India is at a starting stage right now. Only some campuses have MTech. One is mine, Indian Institute of Space Science and Technology. One is IISc Bangalore, some IIT Madras. And right now all the IITs are starting. But having a minor course and training BTech people is really an advantage. So also good morning to all the other dignitaries who are attending. Thank you for giving me this opportunity. We'll start this session. I'll try to introduce what is quantum technology as a whole, and I'll try to go into the basics of quantum computing because you people are starting to have a course here. Then my presentation will give you a complete overview of what will you go through in your minors and all. I'm starting the session. So basically, how do we see the evolution of computing? You are able to see the slide change, right? Hello?
Yes.
Yes.
We are able to.
Now we are in the tab of evolution of computing. So I expect these people are from ECE, CSE, only IT branches, or mechanical and everything, all the students are also there. Okay, fine. We'll start. Yes. So all the students, a hearty welcome into the journey of this quantum computing. So basically, what do we know about computers is, in 1940s and 1950s, people started using vacuum tubes. The computers are as big as a room around here. Then 1956, from 1950s or 1960s, we started using transistors. These transistors were first created in Bell Labs in America. And the transistors, the creation of transistors has completely changed the phenomena of computers. Right now, we are using laptops and our systems only because of the discovery of transistors. Then putting some tens and hundreds of transistors onto a single chip created an integrated circuit. Then we have to go to microprocessors, where we are now inducing billions and billions of transistors, billions of switches onto a single 1-inch chip. So whatever our computers, whatever the processors we use, Intel processor or AMD processor, any processor we use will have billions of switches or billions of CMOS, etc. All this has come from the single evolution. So this evolution has took us around 50-60 years to be in this stage right now. So what next? As already in the previous lecture, Rgukt Subramanian sir mentioned about Moore's law. I want to say it is a privilege to have Rgukt Subramanian sir. We have him in our CDAC lectures actually. So it is a really good privilege for the students to gain knowledge from the likes of people who are heading India Quantum. That is very great actually. So as he said, there is a Moore's law. For every 2 years, the computer speed up. For every 18 months, the computer speed up. So somewhere we have to reduce the size of transistors which are on a single chip. So once we reduce the size to nanometer level, once we try to induce billions and billions of transistors, we have to reduce the size of the individual transistor on the chip, and somehow we'll come into the quantum effects. So if you're reducing the size of the transistors, the quantum effects will come into picture. These are the fundamental effects of the nature. These are happening in the nature. We don't see quantum effects in our day-to-day life, but the subatomic particles on which we are made of, they behave differently. Sorry? Yeah, I'm fine, right? Yeah. So they behave differently than what we behave. They exist, they behave differently, their properties are different, and all these properties, while finding out and through discovery, we had started our journey to the quantum computing. So what do we know? These are our classical computers, our phones, our laptops, and they are all based on very large scale integrated circuits. All our computer ecosystem, we call it classical computers because we are working on quantum technology. So these are all classical computer system. Yes, these has changed the world. They have changed the world significantly. The whole businesses are happening, the whole internet is happening, everything is happening. The last 50, 60 years, and most importantly, the last 20 years, everything has changed because of the advent of internet and because of the advent of accessible classical computers. So this has changed a lot. The businesses have changed, everything has transformed. So a technology, once it comes out of the lab, it becomes economy. So the next economy is quantum computing. So the computers, classical computers use transistors. The scale of the transistors rapidly reaching quantum dimensions, as I have said earlier. When the integrated microprocessor circuit was first made in Texas Instruments, Moore's law came into picture. He predicted that every 2 years will have a speed up. When the number of transistors goes down, so does the overall dimension. Yes, the transistor size is approaching the quantum dimensions. So we will go to affect the quantum, we'll have to see the quantum effects onto the transistors. So we have to have a new approach and a new computation. We have some limitations of classical computers. What are they? Binary processing, which means a classical transistor is a switch. It can be either 0 or 1 depending on the electrical impulse you give it to it. So it can be 0 or 1. It limits the processing state for one state at a time, even in the parallel systems also. What is a scalability issue? As problem grows in complexity, simulating molecules or simulating the nature will become a massive task. Classical computers will take millions of years to simulate these kind of simulations, like DNA simulations, chemical simulations, optimizing molecules, etc. There are inefficient algorithms like cryptographic algorithms. We believe they are efficient because right now classical computers cannot crack this. We need to solve largest prime number factorizations, and it will take millions of years for classical computers to solve these kind of problems. But once the quantum computer comes into picture, the power of its computation is exponentially sharp, exponentially large, that we can solve, we can crack this cryptography. The whole internet, the whole payment system and everything is running on this cryptography only. Simulation of quantum systems. The simulation of quantum systems is also extremely hard on classical computers because the quantum system evolves in a Hilbert space. If you have a 2-qubit system, if you have a 1-qubit system, you have to represent it in a vector of a vector of a single column and 2 rows. If you have 2-qubit system, you have to represent it in terms of a column vector of 4 rows and 1 column. If you have 8, you have to represent like that. So for every qubit, the memory we need is doubling. So we cannot represent classical quantum systems on a classical computers. There is a limitation. Like my computer can evolve up to 13 qubits or 15 qubits. Supercomputers can evolve up to 30 or 40 or 50 qubits, but over which we cannot evolve the state of quantum systems on a classical computer. And energy consumption, everything is also very high. So what do we know about quantum technology? Quantum technology is a multidisciplinary field. Yes, it is really a multidisciplinary field encompassing quantum physics, computer science, and a whole lot of engineering. You need electronic engineers, you need electronics and communication engineers, you need computer science engineers, you need mechanical engineers. This is really a multidisciplinary field. You need engineers who are efficient in vacuum systems. You need engineers who are efficient in cryogenic systems. So this is a complete multidisciplinary field. Electronic and mechanical information are all governed by classical laws of physics, whatever we are using right now. But quantum technology has to alter this scenario. Research and development in this field continues. This will resulting in have its impact in how we analyze data, how we design instruments, how we communicate, how we conduct the financial transactions, everything. So the quantum computing is going to change everything. But as Elvisa mentioned earlier, we have to work on both. We have to work on classical computers and quantum computers. So the quantum computers are particularly used to solve fundamental problems which classical computers cannot solve, but the classical computers will remain into picture. So that is the case. So what are the 4 brief areas of quantum technology? The very 4 brief areas are quantum computing, quantum simulations, quantum communications, quantum sensing and metrology, quantum materials and devices. So quantum computing is of designing qubits and doing computational operations on a quantum computer. Quantum key distribution and all these comes under quantum communication. So quantum key distribution protocols are used, they will give you natural way, they'll give you a natural protection against the hacking of communication systems. Quantum software and quantum clouds, we are using IBM cloud, etc., and we are also developing cloud system for our CDAC computers. Then there is a post quantum encryption. Because quantum computers can crack the classical encryption, we need a data to be prepared in such a way such that even quantum computers cannot crack it. So this kind of theory, this is a whole new set of theory, comes under post-quantum cryptography. Quantum sensors and atomic clocks. So this comes under quantum sensing and metrology. Quantum sensors, they are very efficient. There is a classical limitation. If you people are doing IoT, if you people are doing something, you will use some sensors like UV sensor, sonar sensor, etc. If you're doing basic IoT projects, these are all classical sensors. They work on basic principle. The sensing information is converted into electrical impulse and it is rated as a digital input, or else the digital output is given to the sensor as a electrical impulse. So okay, this is fine. The sensors are gradually changing our lives. The sensors have already had many impacts on our life, but what we miss in this sensor is particular precision. They have a limitation. All these sensors will have a limitation called classical noise. Beyond this classical noise, in order to detect faintest of the faintest signals, and in order to detect things between classical noise and quantum noise, we need devices of quantum sensing and quantum metrology. We have to use them in atomic clocks. Also, if you people are science enthusiasts, you might have known about this experiment called LIGO, Light Interferometry Gravitational Observatory in America. So what they detect is in 2015 or 16, they have detected gravitational waves. And that was a huge discovery that was predicted by Einstein. And after 60 years, they have discovered in 2015 or 16 in that time. What they use is, recently they are improving their systems using quantum sensing to detect even the faintest of the signals from the universe. So this is a case. In order to understand ourselves, in order to understand the universe, in order to understand how we born and why this is all here, quantum technology will be very helpful. Quantum materials and devices. In order to run devices of quantum computation, we need quantum materials. What are quantum materials? Superconducting qubits, nano diamonds, so lab grown diamonds, NV centers inside the diamonds. These kind of things are used in quantum materials for single photon detection or single photon control of photons. And quantum superconducting qubits are used as quantum qubits. Microsoft is working on topological qubits. So all these kind of things come under quantum material and devices. It is good that RGKT 4 campuses have chosen one of each technology domain and they are working on it. What does the quantum technology promise over classical technology? So it does promise an exponential increase in computational speed for certain problems. Yes, the ability to break classical crypto systems, high degree of information security guaranteed by the laws of physics. In the previous slide, we have discussed about quantum key distribution. So the protection is given by the nature itself. We don't have to add an additional protection to the data that is sent using the quantum key technology. The protection is fundamentally given by the laws of physics itself, so which cannot be cracked. And we get exquisite, sensitive and accurate measurements, that is using quantum sensing devices. We have improved atomic clocks. Everybody might have a small understanding of what atomic clocks are. These are sent into the space. They will track the time to the very precise limit. So over these atomic clocks only, all our transactions and everything, all the internets will run through. So what if we get more precise atomic clocks? We can have more precise calculations. We can have more precise data transfer, and all this can be improved. So then what can we do with quantum technology? We can design and discover new drugs, because classical computers are taking millions of years to simulate, whereas the quantum computers can simulate the same phenomena in days or in hours. We can actually have new drugs or new chemicals discovered, and that can improve the health status of the whole world. We can have an idea of financial markets, space applications, and even genetic applications. So these are a basic idea of what quantum technology can do. Yeah, this is all exciting and thrilling, but there are its flaws also, which we'll discuss in the next slides. So this is a major idea in how many industries the quantum will impact. So it can impact chemicals and petroleum, distribution and logistics, financial services, healthcare, manufacturing. In algorithms, it can do chemical simulations, AI/ML algorithms, optimization can be used. So all these kind of horizons can be changed using quantum computation or using quantum technology as a whole. So how did it all begin? There has to be a beginning for everything. So this all began in 19th century, where people thought, or scientists thought, that classical physics and electromagnetic theory can explain everything. So scientists thought that only precise measurements are pending, but nothing is left out. The whole physics is complete. But the nature said, no, physics is not complete. Scientists started to observe abnormalities in experiments such as black body radiation. So black body radiation, with the calculations they done, scientists have predicted an ultraviolet catastrophe. It has to emit infinite amount of energy, but emitting infinite amount of energy is against the nature. So the calculations were wrong. Then Rutherford's atomic theory has, if we believe in the Rutherford's atomic theory, which you might have learned in your 10th class or 12th class, that is the first atomic theory. It is appreciable, but if we go into Rutherford's calculations, the electrons should not stay in stable orbits. They have to fall into the nucleus and the atom should collapse. But that is not happening. Electrons are stable. This is where classical calculations have failed, because the nature is exhibiting a different behavior than the classical behavior. Scientists observed these hints that, and then they thought that classical physics cannot explain these kind of phenomena, and they started discovering quantum phenomena, quantum effects, quantum computation, quantum mechanics based on these experiments. So the experimental observations, also the main experimental observations such as photoelectric effect, for which Albert Einstein got Nobel Prize, Bohr's atomic model, these all led into the quantum theory. So this is the very beginnings of quantum theory. The quantum theory was almost discovered in 1910s, 1920s. Then finally, we came to a conclusion that subatomic particles behave differently when compared to the objects with which they are made of. So we are behaving differently, but the subatomic particles on which we are made are behaving differently. Dual nature of matter was observed. For all the time, for all the previous to the quantum, observing quantum effects, people thought light is a wave. Then, yes, but after observing quantum effects, we have theorized the dual nature of matter, which actually is, so in the dual nature of matter, we can conclude light as a wave. How to conclude light as a wave? Because we experience the phenomena such as superposition, interference, diffraction effects of light, which explains the wave behavior of light. And what theory explains the particle behavior of light? Photoelectric effect. So the photoelectric effect, only after certain frequency the electrons will come out of the steel plate, only after certain threshold. So what happens? It behaves both as a particle and as a wave, and the fundamental particle of a light is photon. Is this same with all the matter, electrons, protons, neutrons? Yes, they all behave in a dual manner. That is observed through double slit experiment, which is also one of the biggest experiment that confused the scientists and also led to the dual nature of matter theory. Scientists observe peculiar behavior not only in wave particle duality, but also in phenomena such as quantum tunneling and quantum entanglement. So this entanglement phenomena is what the whole quantum communication is dependent on, which we'll see in the next slides. So all these principles, all this, they led to an idea famously quoted by scientist Richard Feynman: nature is quantum. We need our computers to simulate nature, which is we need quantum computers. So this was in some, this idea was popped up by Richard Feynman in some 1980s in some conference where all the computer scientists, physicists, mathematicians have came and gathered, and they were discussing about reversible computation and the idea of simulating nature. So in order to simulate nature, you have to design a computer that follows the laws of nature. The laws of nature are quantum. So that is how the idea of quantum computing began. What is quantum computing? Quantum computing is a type of non-classical computing based on the quantum states of subatomic particles. The behavior is governed by the laws of quantum mechanics. Quantum computing is fundamentally different from classical computers. which operate using binary bits. Even the quantum computer uses binary bits 0 and 1, but the quantum computer has a property of superposition. It can be 0 plus 1 at the same time. In quantum computing, the bit is referred as a qubit. So unlike the strictly binary bits of classical computing, qubits can strangely represent a range of values in one qubit. This representation is called superposition. So the effect of this superposition is improving the computation speed of quantum computers. Superposition is what gives the quantum computers speed and parallelism. Qubits can be linked with other qubits in a process called entanglement. When combined with superposition, quantum computers can process a massive number of possible computations at the same time. So if like for example, if I have like 5 qubits or 10 qubits, I can do 32 calculations, 2 power 5 at the same time, at the same moment, in the same stretch. Whereas if I have 5 classical bits, I have to wait for 32 calculation, 1 calculation, 2 calculation, 3, like that I have to wait for 32 calculation. So this calculating massively in one stretch is where the computational speed of the quantum technology lies. The number of high quality qubits is necessary to make a viable quantum computer. Yes, that is the problem right now. How much stably we are keeping the qubits is the fundamental question right now. The ability for quantum computer to outperform classical computer is called quantum supremacy. So what happens is when a quantum computer solves a problem within a day or within weeks, which a classical computer, which the world's fastest supercomputer can take millions of years to solve, then that is what we call as quantum supremacy. Because it's like it's saved this much exponential of time. We don't know what massively we can do. Like if we have 150 or 200 qubits, we can simulate almost anything. So this kind of quantum supremacy is what making the people excited about quantum technology. They are investing billions of money. Countries are investing billions of money to solve. Even private big firms are investing billions of money to build an efficient and stable quantum computer, because quantum supremacy can solve all the problems which classical computers could not. So what are the basic quantum mechanic principles? All we have been discussing in the previous slides: superposition, quantum tunneling, and quantum entanglement. Superposition. The principle of quantum superposition states that if a physical system may be in one of the many configurations, then the most general state is a combination of all these possibilities. Yes, superposition is a combination, a linear combination of all the physical, of all the states that a physical system can be in. Quantum tunneling is a quantum mechanical phenomena where a particle passes through a potential barrier which it classically cannot. So classically, if you have to take a diode, for example, diode is a switch. Like we have to give an electrical impulse of 0.7 electronic volts for a silicon diode for jump from 0 to 1, for low state to high state. So this kind of jump can be passed using quantum effect. So the quantum particle, sometimes through quantum tunneling, it can pass through this potential barrier. So that effect will also come into picture. Then quantum entanglement is a very interesting phenomenon. If you take two fundamental particles like two electrons, and if you try to match the properties, such as, you know, the properties of electrons, right? If you know the properties of atoms, so they are described by 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So the spin up and spin down will decide in what spin an electron is in its orbit. So if I match the spin of 2 electrons, if I somehow match the property, spin or any property, but mostly spin. So if I match the properties of 2 electrons, and if I take 1 electron with me, and if I keep another electron at RGKT campus, if you change the property of that electron, the electron in my hand will automatically change. The property of the electron in my hand is automatically changed, which means even if these 2 particles are very far apart, they behave as one. They both are defined as one. That is a fundamental definition of entanglement. So they both are defined as one, and changing one will instantaneously change the other thing. But people will get a question: does it violate Einstein's theory of relativity? No, it doesn't violate. The particles will change automatically. But for you, in order to observe it, we have to communicate in only the classical case speed of light. So it does not violate Einstein's relativity theory. So because even if the particles change, for us to observe, for us to communicate, we have to communicate within the limit of classical light, within the limit of speed of light. So these are the basic quantum mechanics principles which excited everybody to develop a quantum computer. What is a brief history of quantum computing? As I said, in 1982, Richard Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of laws of classical physics. Then, after this, in 1985, David Hughes developed a quantum Turing machine and showing that quantum circuits are universal. So all the quantum circuits are universal, and David Hughes has also developed an algorithm called Hughes algorithm. It just is it's the first algorithm you learn when you start quantum algorithms. Actually, it is very easy. It just explains the superposition principle. It just explains how a quantum advantage can be gained. And this is the very important step. In 1994, Peter Shor came up with a quantum algorithm to factor very large numbers in polynomial time. This will shatter our classical cryptographic systems like RSA cryptography, elliptical curve cryptography. So they are developed on the fundamental idea that they can take millions of years to solve, which means it will take 10 years or 20 years. After 20 years, your data will become obsolete. So, but what happens in a quantum computer is they can be solved in polynomial time, within days or within weeks or within hours. This will create a serious threat to our cryptographic systems. Then Love Grover developed a quantum searching algorithm which will reduce the time by root n times. So it is for basically a search of database will take the largest time complexity is big O of n. But he developed an algorithm in which the search algorithm will search the whole database within big O of root n time. All these are quantum algorithms you will next learn in your quantum course, in your quantum minor course. These are the basic fundamental algorithms. So all this will take quantum effects into picture. So basically I'm talking about qubit. So these are the fundamental bits and they take same as classical bit, they can take value 0 and 1. They are represented in bracket notation. This notation was first developed by scientists itself, Paul Dirac and all. So the bracket notation is represented. This is called ket 0 and this is called ket 1. So what is a ket? A ket is a basic column vector. So the ket will represent the ket is a single 2-row single column vector. So ket 0 is column vector 1 0. Ket 1 is column vector 0 1. So this represents the state of the quantum system. It is different from the classical qubit in a property called superposition, where the laws of quantum mechanics allows the qubit to be in the superposition state of both 0 and 1. All the distinct states of 0 and 1 can be visualized using the Bloch-Spear unit. 0 and 1 are called computational basis states and are represented on the z-axis of the Bloch-Spear. The Bloch-Spear, which we'll see in the next slide. So 0 and 1 are the computational basis states which we'll work on. There are other bases also. There is x basis and there is y basis. So the other basis is ket plus. This is x basis. This is the superposition 0 plus 1 by root 2, which means it has 0, 1 and all the possible cases of all the values in between. Minus case is 0 minus 1 by root 2, ket 0 minus ket 1 by root 2. This is represented on x-axis of the Bloch-Spear. Whereas we have another basis on the y-axis of the Bloch-Spear, which is plus I and minus I. Ket plus I will represent 0 plus an added phase of I, ket 1 by root 2. Minus I will represent ket 0 minus I ket 1 by root 2. So these are all the fundamental basis states which we can represent in the Bloch-Spear. So the superposition state is plus state, minus state, plus I state, minus I state. We have to first define the quantum qubits. Every qubit should be defined in a 0 state. From the 0 state, in order to gain the quantum advantage, we have to prepare the states into a superposition states, for which we have to use quantum gates. So basically that is the thing, right? If classical gates, we have NAND gates, NOR gates, etc. For generating an output, we have to use these gates. So for classical adders, classical subtractors, we use NAND gates, NOR gates, everything. For quantum gates, in order to put a quantum state into a superposition state in which all the possible outcomes are present, we have to use a gate to put the quantum state into that superposition. So for the representation of simulation, quantum gate is called Hadamard gate. So this Hadamard gate will put 0 state into 0 plus 1 by root 2. So, but what happens in a real physical quantum computer? How do you put a state in a Hadamard gate? I cannot, this gate H will have a physical meaning. What is it? It can be a microwave pulse. For superconducting qubits, we use microwave pulses as gates. Yes, this is fundamentally different from all the CMOS processors we are using, but that is how the case is. So the physical representation of all these gates in an optical quantum computer, if you want to use a Hadamard gate, the optical quantum computer, you just need to have a you just need to have an optical device which will act as Hadamard gate. If you send a photon from that device, it should either give one path or other path. So either after hitting the device, the photon should come from one side or the photon should come from other side. So this kind of non-clarity of where the photon will come out after hitting the device is where the superposition lies in. So there are different ways to generate superposition, but classically, theoretically, they're all defined in terms of gates. So we'll see the gates in the next slide. So basically, qubits are represented by kets. So our whole quantum states is represented in terms of this formalism. Ket psi equal to alpha ket 0 plus beta ket 1, where alpha and beta are complex probability amplitudes of the qubit, which will determine the probability of measuring ket 0 or ket 1. So finally, after generating all the results and everything, we have to measure the quantum state. So when we have to measure the quantum state, the alpha and beta will come into picture. We'll have to do mod square of alpha and mod square of beta to know how much probability of the state is in ket 0 and how much probability of the state is in ket 1. So basically, it should satisfy this identity, alpha square plus beta square equal to 1. Measuring a qubit whose state is given by will yield the classical value of either 0 with probability alpha square or 1 with probability beta square. The measurement is completely random. So this is another feature of quantum computing. The measurement is completely random. If I measure this state, I'll either get 0 with probability alpha square or 1 with probability beta square. So this is a fundamental randomness given by the nature. So for example, take this quantum system. So just assume that this is a nucleus and this is where the electrons are around the orbit. So this is not general exact representation, but a visual representation for you to understand how can we simulate quantum computers. So let us assume this orbit 0, which is near to the nucleus, is ket 0. This orbit is ket 1. So this is 0 state of our computer. This is 1 state of our computer. I'm clear until this, I guess. So our computer state can be represented in alpha ket 0 plus beta ket 1. So as I mentioned earlier, ket 0 is a column vector of 1 0, ket 1 is a column vector of 0 1, and the whole psi is represented in terms of column vectors as alpha and beta. This is same, just substitute 0 here, substitute the 1 here, you'll get the psi as alpha beta. So that is the state of single qubit quantum system. So what happens is, let us assume my electron is a qubit. So my electron is in the state 0. So if the basic simple question is, how do I move this electron from the state 0 to the state 1? I have to give some energy. So that energy can be in terms of some impulse, some photon energy. So I have to give some electron volt energy for my electron to jump from 0 state to 1 state. Some pulse, some electrical pulse, some microwave pulse, some photon pulse I have to give for my electron so that it will jump from 0 state to 1 state. But as we know, 1 state is not stable. It will come back after certain time. So between that time only we have to do our calculations. So this is how the precise measurements of quantum will take place. So between because 1 is not the stable state of my electron, it has to definitely fall back, or else it will violate all the classical all the quantum physics principles. So it will fall back after certain time. But what if I have to keep this qubit which I have in a Hadamard state or a superposition state? So general idea is a Hadamard is 0 plus 1 by root 2. It has to be in both, it has to have the details of 0 and the details of 1. So what will I do is, if my electron is in 0 orbit, I'll give half electron volt energy so that the electron will jump from here to somewhere in between the orbit. Now
we don't know where the electron is in. The electron can be in 0 or the electron can be in 1. So this kind of principle is where the superposition effects will come into picture. So how the quantum computing addresses the limitations? Superposition will give you exponential speed up of the time. So superposition will allow you to have a vast number of calculations at once. For classical computers, we do one calculation at a time. But here, because of superposition, we can do 20 calculations, 30 calculations on a single instant, 100 calculations, billion calculations also. That will give you a massive output. Then entanglement, very briefly I have explained to you about entanglement. So entanglement is very helpful in communication systems, and it will help in more complex computations also. Quantum parallelism. Quantum computer can explore many solutions instantaneously. That is what superposition is all about. Efficiency of quantum systems. Since the quantum computers operate on quantum principles, they are naturally suited to simulate molecules, atoms, and other quantum systems. This is what we are talking from the first. In order to simulate nature, we have to design a computer that follows the fundamental laws of nature. So that is quantum computing. Quantum computing isn't here to replace classical computers entirely. Yes, it is more like a powerful new tool for the problems that classical computers cannot crack efficiently. So this is the basic representation of a block sphere. So block sphere is for our visual understanding. So it has 3 axes, Z, Y, and X. So this is Z state, ket 0, which is a fundamental state, and opposite to it, exactly 180 degrees to it, is ket 1. So these two are computational basis states. As I have discussed in the previous slides, there are other basis states. So they are plus X, plus, ket plus, and ket minus. They lie on X axis here if you clearly observe. Then there are state ket plus I and ket minus I. So this state lies on the Y axis. So this is how we represent a single qubit gate operations are rotations on the block sphere. So using the rotation angles like theta and phi, we can represent all the gates and all their behaviors happening on a block sphere for our understanding. So what if I use a Hadamard gate? If my my qubit is in 0 state, and if I use a Hadamard state, by using Hadamard state, I am expecting it to be in a superposition state. I am expecting the quantum state to be in a superposition of 0 plus 1 by root 2, so that I can continue my calculations. So I can calculate on both 0 and 1 if it is on superposition state. So basically, if I give a Hadamard gate, which means it is rotating 90 degrees in this axis, in the Z axis. So from Z, it will come to plus state. So plus state is my Hadamard state. So by every operation of gates can be visually represented using block sphere. This is for our understanding. That's it. So yes, we have come to this slide. So basically, in classical systems, if you are doing digital design, digital system design or something, you might have in your coursework CSC, EC, and EEE people. So there you use NAND gate, NOR gate, AND gate, OR gate, XOR gate, everything, etc. So these gates are what are running in our classical computers on the laptops right now on which we are viewing this lecture. They are all running on classical gates, and these classical gates are not reversible. Why they are not reversible? Because for example, take an AND gate, A and D, AND gate. So 0 and 1, if I give to the AND gate, it will become 0 in the outside. So I am giving 2 inputs, I am only getting 1 output, which means the information is lost in the form of heat. So as the information is lost, we cannot bring back the original states. So they are not reversible. But the main idea of quantum gates are, they are reversible. The quantum mechanics runs on the underlying principles of unitary and Hermitian matrices. So these gates are reversible. We know the input states, we know the output states. We can go from input to output states, and we can trace back from output to input states. So this is the fundamental principles of reversible gates also. So yeah, this is a new concept, but all the quantum gates are reversible gates, because an ideal quantum system should follow this principle. So all the gates are reversible. So what do we have? Poly X gate, Y gate, Z gate. So X gate is our basic NOT gate which we represent. What happens in X gate is simple. If my state is in 0, ket 0, if I apply X gate on it, it will have to jump to ket 1. So this is like classical NOT gate. So same with Y gate, Z gate, etc. Z gate will induce phase, Y gate will induce phase and also will flip the qubit. Hadamard gate, which we all are discussing about, all these gates are matrices because our quantum system is represented as a column vector. Any multiplication happening in a column vector should be a matrix. So all the gates are represented in the matrix systems. So, and there are control gates, which means you can hold one qubit as control and you can target another qubit. If one qubit is 0, other qubit won't change. If the control qubit is 1, the other qubit will flip the bit. So this kind of gates can be done. Swap gate is there. Toffoli gate is double control gate. X1 qubit will control, X2 qubit will control, and X3 will change. X3 will flip. So these kind of gates are developed in the quantum systems. So this is a basic example of a block sphere. If you are starting at ket 0, then if you are applying Hadamard gate, this will jump from 0 to X, 0 to plus. So this is a plus state we have seen in the previous slide. So plus state is a superposition state. If I apply Z gate to the plus state, it will has to rotate 180 degrees and it will go to minus state. So minus state is 0 minus 1 by root 2. So a phase difference in the superposition. Then if I apply H gate again, it has to jump to one state. So these kind of representations can be done on a block sphere. So basically when you're doing operations, when you're using quantum simulators like IBM Qiskit, or even you can use our CDAC simulator also, QSIM. So the block sphere representation will automatically pop out for you for better understanding. What are the fundamental use cases of quantum computing? They are superior efficiency and exponential scale capabilities, quick detection and diagnosis. So detection is using quantum sensors, then transforming machine learning and artificial intelligence capabilities in multiple times. So you're processing a huge data on in a single stretch. So this will improve the efficiency of machine learning systems. Finance systems you can do, protection of government data, we can secure government communication systems and data systems. Then we'll solve the behavior of nature actually. Then we'll use quantum cryptography. Then this can be used to generate economic growth and social growth. So these are the use cases of quantum computing. So the quantum computing will have key potential applications. For chemistry, we can work with 100 to 200 qubits. For optimization problems, we need 100 to 1000 qubits. For machine learning also, we need 100 qubits to 1000 qubits to process a lot of data and generate an output, efficient output. And for material science, in order to develop new materials and new strength materials, we need 100 to thousands of qubits. And in order to solve the unknown problems in the nature, we need some 1 lakh plus qubits. People around the world, Google, IBM, everything, etc. Every day, every moment, they are improving their quantum systems. So somewhere, as earlier Elvisa said, somewhere by 2033, we can see some good amount of stable quantum systems. Now we come to the picture. I have given you the idea of what a quantum bit is. I have given you the idea of how all this quantum technology began. I have given you idea of what are the main core technologies in quantum technology. But let us see, how do you physically realize a quantum computer? A quantum computer realization is not as simple as this classical computer. Around the world, all the classical computers we are using, all the laptops we are using are defined on a simple, same architecture, singular architecture. But the quantum computers, because we see quantum effects in various forms in the nature, we have hybrid quantum computing platforms. One of the platform is superconducting quantum computing, which IBM is working on it. So in superconducting quantum computer, we'll use Josephson junctions. So these Josephson junctions are very simple. Superconducting material, a superconducting material, and a small insulator in between. So same as semiconductor, we have superconducting bits. So basically a semiconductor, an insulating layer, and a semiconductor is a transistor, and it will act as a switch. Same here, a superconducting layer, a small insulator, and a superconducting layer will act as a qubit. So all these 4 qubits, four of these qubits will become a logical qubit, and will operate on these qubits not using electrical pulses but using microwave pulses. So we'll have to bombard these qubits with microwave pulses, and then we'll have to extract the output from these qubits. So it is fundamentally very different from how classical computers work. Then we have trapped ion classical computers. We use heavy magnetic fields to trap some ions, some 10 ions, 15 ions, etc. we use heavy magnetic fields from all the direction to tap some ions, and then we'll use laser pulses to simulate these ions to put them into Hadamard states to carry our to carry our computations. So trapped ion is also, it requires a huge setup. So it is a very expensive setup. Even superconducting is also an expensive setup. So they require heavy amount of engineering and precision. That is what I'm actually trying to say. So these trapped ion computers, quantum dots, cold atom computers, superconducting computers, they're not simple computers that we can bring onto a table. They need extreme effects. First thing is, what we are working on is fundamental particles. We are literally creating atoms for computation. So either we are using atoms or we are literally creating particles that behave as atoms for computation. So atoms are always very, very, very unstable. They cannot be controlled in room temperatures. So because the room temperature is around 27 degrees for on an average, or 30 degrees centigrade, the atoms will vibrate. The information can be lost in form of heat. We cannot put the atoms in a stable state in the room temperatures. So here comes a picture. We have to cool down. We have to cool down these entire systems. So these systems will use vacuum systems in order to remove particle dust and everything. The vacuum systems are so efficient. The vacuum systems which you use here are almost related to the semiconductor manufacturing facilities. So, and also here we have to use cryogenic systems. We have to reduce the vibrations in the particles, the vibrations in the qubits, into such a small level. We have to actually cool down to 99% of fundamental limit of temperature, fundamental Kelvin temperature, minus 272 degree, 272 Kelvin, minus some nanoscale or microscale. So we have to cool down such that the particle vibrations will stop, the particles will be stable, and we can do our operations on particles. This is how complicated quantum computing is. The physical quantum computing is very exciting, the physics of quantum computing, because it will actually add multiple domains. We need the cryogenic experts, we need vacuum system experts, we need someone who is experienced in semiconductor technology, superconducting technology. We need to manufacture chips, superconducting chips onto a small layer. So these kind of things, and we need to also convert analog to digital and digital to analog. So what we are typing in our computers, if I am typing a quantum program, that is a digital code. This code has to be converted into analog, and these analog pulses are to be given to the superconducting qubit. So these analog pulses are given to the superconducting qubit through wires. So microwave pulses, our whole code is transformed into microwave pulses or photonic pulses, and these pulses are given to through the wires, are sent to the quantum chip, which is residing inside a cold chamber, and from there we'll get our data back from analog to digital again to see on a physical computer. So this is how the complex this system is, and this is how exciting this system is also, because we don't right now we don't see how many zeros and ones. For million, if we want to do million calculations, we just have to send million pulses. So it's about sending pulses. This will completely fast the calculation operations. So if time is there for an industry visit, please go and see superconducting quantum computer setup in IISc Bangalore. It is there, and some of the labs it is there. For cold atom setup or trapped ion setup, IISc Pune is working on it. So these kind of complicated setups are there to physically realize the quantum computers. So superconducting, yes, superconducting materials use niobium, and which exhibit zero electrical resistance at low temperatures. Semiconducting quantum dots we can use. Quantum dots are just artificial atoms. We just reduce the size of the semiconductor such that we can operate on 1 or 2 electrons. Trapped ion systems are confined, the ions are confined, they are holded together using electric fields and magnetic fields in a vacuum chamber. Photonic qubits are using laser pulses and non-linear optical devices and optical devices. Then nitrogen vacancy centers are used for detection. Nitrogen vacancy center are also is to control the single photon evolution also. People claim that they are very stable when compared to other qubits, but it is very tough job. It is very, very tough job. Then NMRs our basic NMR devices, which in our medical hospitals and everywhere we use, these NMR devices, they are also used in form of qubits. So what does basic NMR do? It resonates with the spin of electrons in our body. So it is simple. So that is how they detect any anomalies in our body. It resonates with the spin of the electrons of fundamental particles in our body. The same thing, the same resonance of spin can be used to generate qubits. So these are all the hybrid structures of what qubits are. But as I am telling you, this is not simple. This is not exactly easy, because there are many obstacles in order to develop and generate an efficient quantum computer. First thing is scalability. Scalable physically, in order to increase the number of qubits. So controlling qubits will become tough in order to, if we increase the number of qubits. Then qubits has to be initialized to arbitrary values. You don't know whether the qubit is in 0 or 1. You have to, the initialization of qubit is also a difficult process. Then quantum gates should be act faster than decoherence times. So basically, if I have to send an electron from state 0 to state 1, where the state 1 is not fundamentally stable for electron, it will fall back. My calculations have to be completed before it falls back. So I have to do calculations in that fast manner, and I have to run my race through decoherence and dephasing, etc. All these errors will come into picture. Even with minor electrical vibrations, minor errors in the nature around will disturb the quantum system. So it has to be physically in a very secure place. Qubits that can be read easily. So reading of qubits is another problem. As I have said earlier in the architecture, first our code will convert into microwave pulses. These microwave pulses will go on to the qubit chamber, and from there they resonate, and the resonated pulses will have to see the output. So this is a long, lengthy process. So reading we have qubits is also a very difficult challenge. Then sourcing the parts of quantum computing. So we have to really innovate new computer parts we have to really innovate new parts, new objects of quantum computing in order to work for the efficient quantum computers. So where do we stand today? So what is our current goal right now? We stand in noisy intermediate NISQ era. People are good with 50 to 100 qubits, and as there is a setup of 150 qubits at one of your campuses, which I've heard from the previous lecture. But this is exactly not a lot of qubits. When you have a lot of qubits, and controlling each qubit will be a difficult task. We need error correction to deal with the errors, and that is why we require many more physical qubits. Combination of physical qubits will become a logical qubit, and on this logical qubit we have to operate. So it is a whole different business. You will go into depth in your minor course, but you will come in at the end of your minor course. You might come into quantum error correction and all these principles. But this is how it is. It is complicated. It is not easy. It can be used. It cannot be used in daylight natural temperatures. It has to be in a secured chamber. But we are doing it because it shows us a promise that it will solve some of the fundamental problems that we are striving for. Then what are the frameworks? If you want to practice quantum computing as a simulation, it is very easy. It is just a Python code. You have to just understand how to put your quantum state into superposition. Then you can carry on your calculations. So what are the frameworks that are available in the in the websites today? Qiskit is there, IBM's Qiskit. This is very famous. Everybody is doing it. Google Circ is there. Then Rgukt, Q-Sharp, Project Q, D-Wave system is there, and everything. And also these are the resources for Qiskit. These are it's fine. You can just directly go on Google, you will find it. So for quantum information and quantum computation, I'll suggest you go with easy books. This is one of the top standard book and one of the hardest books to extract information from. So when you're preparing a syllabus, you can go with easy books actually. So what at CDAC we are doing is, we also have a simulator called QSIM. So all the other simulators in the world are using state vector simulations. We are going to density matrix simulations. Through density matrix problem, state vector and density matrix basically represent the same quantum state, but having the representation in density matrix will give us more efficient understanding of errors. We can induce errors, we can induce noise parameters, etc. So for having this kind of efficiency, although it is very heavy when compared to state vectors, although it will take a lot of time and only we can simulate half of qubits of state vectors, we actually designed a quantum simulator using density matrix. in association with IIC. The backend, the whole mathematics process was with IIC, IIT Roorkee, and we are actually having it on a website called QSIM. You can go to Google and directly type QSIM. There also you'll find a lot of interactive things, examples, algorithms, etc. And you can give it a run, and we are running it on our supercomputers and clusters. So this is how it is. So this is how the basic quantum circuit, this is how the code will be. So in this code, we have to define a quantum register, we have to define a classical register, and because the outputs have to be read through classical registers, that is how the nature is. The output has to be read through classical registers. So the operations will happen on quantum registers, and after measurement, we'll only get one output of all the many possible outputs into a classical registers. And here is a trick. We have to use our gates such that we should get the output what we want. We should get the maximum optimized output. So the outputs are taken to the classical registers, and this is how a quantum circuit is. So we can induce the noise parameters in our simulator QSIM. Rotation error we can improve, and this control gate error, decay error, depolarization error, decoherence error, thermal factors. These kind of noises we can induce and see how the quantum systems are behaving. So this is the code. We can do single qubit measurement in different bases. So this is how an actual quantum gate looks like. So this is Q0, Q1, Q2, 3 qubit system. So for 3 qubits, we need 3 classical registers, C0, C1, C2. These are all the gates. See, for example, this is the X gate, this is the unitary gate, this is control not gate, rotation gates, etc. So this is how the quantum system looks like if you're preparing a quantum system. What will it execute is, it will execute it in a timely basis. So first it will execute all these gates, then it will execute all these gates, then NOT gate, then U3 gate, then again NOT gate, then U1 and X gate, X and U1. So it will execute it in a timely basis, in a step-by-step manner. So this is, you can go to the QSIM website, you can work on it. Examples are available, simulations are available, everything is available. So finally, I have to conclude with this. What are we working on quantum technology in CDAC? So we are working on quantum accelerator project, especially I am working on quantum accelerator project where we are using parallelization and like OpenMP and MPI kind of concepts to improve the speed of the quantum simulator, which I have introduced you in the previous slide. QSIM. Quniverse is a new workout where you can execute your quantum simulations on a CPU, on a GPU, on a tensor processing unit, and also on a quantum processing unit, QPU. So all these kind of hybrid processes are included in the Quniverse website. Then we are working on, we started our basic steps on quantum machine learning, and some of the CDAC centers are working on quantum sensing and photonic quantum devices, etc. So this is how it is. I'm very happy to have this lecture and share this knowledge with you. This is an exciting field, and this is a hard field also. It is not easy. You cannot, it is not a UI design. It is not as simple as that. You have to do hardcore mathematics. If you are interested to make a change, quantum technology is one for you. And all the best for all the students who are starting the minor in it. And also all the best for RGKT administration. Thank you from my side for giving me this opportunity.
So thank you, sir. Thank you for your valuable words. So firstly, I'm a person with no prior knowledge in quantum technologies, but I easily understood everything you just told right now. And I believe many of our students are feeling the same way. And I believe that our student minds are filled with lots of knowledge from you, sir. So I sincerely thank you for all the time you have spared to enlighten us, sir. Thank you, sir.
Sure. Thank you. So that is the part. Because you are new to quantum technology, we have to make sure that you understand the principles at least. I know maybe half of it or you have understood, I guess. But if you are going into your minor course, you will get more introduction of it. There are a lot of resources available online and offline, and a lot of your faculty are doing great work bringing these lecture series. You have very knowledgeable physics faculty and all. So even we are available from our side to guide you.
Any questions from?
Yeah, any questions I'm ready to take.
Yeah. Not from me.
Good morning, sir. Very good morning, sir.
Very good morning.
Sir, actually, quantum computing is very useful in cybersecurity.
Okay.
So encryption and decryption, large factor numbers.
Yes, yes, yes.
So I think it might be very threaty to cyber threats maybe happen, because how much advantage is there? So such much disadvantage is there.
Yeah, that's a good question. Actually, if quantum computer is in wrong hands, at least not for now, in next 10 years or 15 years, so our cyber security is in a questionable place. From that, at that time, we have to upgrade our systems to post-quantum cryptographic solutions. NIST has already found out 5 or 6 algorithms that are quantum safe algorithms. So people are doing, but we have to shift our infrastructure from normal cryptography to post-quantum cryptography. And also, even though hackers are, even the encrypted data is there, people are saving it. Hackers are saving it. Hackers or government organizations are saving it, so that when an efficient quantum computer comes, they can decrypt it. So all the encrypted data right now, any important data, hackers are saving it. It is save now, harvest later kind of attack people are doing right now. So we have to upgrade our systems, at least our security systems, to post-quantum cryptographic solutions.
Okay, sir. Thank you, sir.
Yes, thank you.
Any other questions? Thank you, Abjit sir. And today, actually, even I am doing QT 00 and 01.
Oh, yeah.
So I feel really good to hear you from the same things. And thank you for the wonderful session. You have given some things which are connecting the physical meaning of a qubit, and which is the moving of electrons from the excited state to the ground state, and explain the superposition and in a very detailed manner. And you have given the insights of this, what are the upcoming challenges and resources also you have provided to us. Thank you so much for coming forward and presenting for lecture series. And thank you once again.
Yes, ma'am. Thank you, ma'am. Thank you very much. Actually, it is actually my way of giving back to RGKT. RGKT is in my heart. It is where I have found my interest of physics, and I have chosen quantum technology. So it is a RGKT is always close to my heart, and I'm always ready to help if anything is needed. Thank you.
Yeah. Please be online for 1 moment.
Yes.